Hello everyone. In this video, we're going to be talking about meso compounds. It's very important to be able to recognize what meso compounds are, and then a lot of times students take those as enantiomers. So there are some criteria that has to be met before you can identify those compounds as a meso compound. So let's jump right into it. For something to be an meso compound, you have to have at least two chiral centers. All right, so if you don't have two chiral centers, if you only have one chiral center, it cannot be a meso compound. And then you could very well have more than two chiral centers, but at least the minimum requirement is going to be the two chiral centers. In addition to that, you must have an internal plane of symmetry. So what that really means, you may have one side of the molecule is a mirror image of the other side of the molecule. And in that scenario, you would have at least, suppose, two chiral centers. Then in one of the chiral center would be R, and the other chiral center would be S. Or another way of saying, if you have, suppose, more than two chiral centers, and we can talk about maybe four chiral centers, then 50% of your chiral center must be R and other 50% must be S so that they cancel one another out. So even though you have chiral centers in the molecule, but then you got a 50-50% of R and S in there, your overall molecule is going to be a chiral, or another way of saying it's not going to rotate the light into a particular plane. So let me take a few examples here just to kind of clarify things. And I'm gonna talk about the Fischer projections and how to use Fischer projections to identify the meso compounds because that's gonna be the easiest one to recognize. And then when you have the bond line formulas, they are a little bit harder to identify. So let's focus on the Fischer projections first. So suppose I got these two structures that are written out here. I'm gonna call this first one as A, call this second one as in B. And if someone asks you what's the relation between those two, and the very first thing that's going to come in your mind, well, they look like mirror images of one another. And that's because if I go ahead and put a mirror in between those two, so suppose this is the mirror I got here, and once I put the mirror in between those two, you see the mirror image of A on the other side. So A and B, another way of saying, are mirror images of one another. But then you want to make sure you double check before you considering those as enantiomers. So there's a couple of ways you can do it. I want to go ahead and draw a flipped version of that right here. So I'm gonna rotate that by 180 degrees. So when I rotate it, how's that gonna look like? I'm just gonna go ahead and maybe make some of these this OH to be shaded here so that you can see how that's gonna be looking like when you do go on the other side. So I'm just gonna go ahead and copy this right here and put it right here. But remember, I gotta raise those and see how that's gonna look like now. So when you rotate it, when you flip it by 180 degrees, your OH is gonna be right here. So that's this particular OH right there. And then right across this, you're gonna have a hydrogen. And then if I look at, maybe change the color here, if I look at this other OH, it's gonna be on right here. And that's gonna be the hydrogen there. And then now you can clearly see when I call this maybe A prime, what's the relation between A prime and the B there? They're clearly not non-superimposable mirror images of one another. And to double check, if I draw a mirror, if I have a mirror right in between the B and this A prime, they are not they're not flipped. And what I can say, if I pick this molecule and if I duplicate it and if I place it right on the top of B, it actually going to be the same thing. As a result, their A and B are not going to be the enantiomers. So if that was an enantiomer, when you flip this A by 180 degrees and you get an A prime, the A prime and this B should have been an enantiomer as well. So as a result, this cannot be an enantiomer, so it has to be an meso compound. That's one way of looking at it, and I know this gets very hard when you're looking at through the mirrors and visually. The second way you can always look through is figuring out the internal plane of symmetry. So if I draw a line right across here, then you can clearly see the top of the molecule is the mirror image of the bottom of the molecule, and that's exactly what you're going to be looking into. So if you have the top portion of the molecule, mirror image of the bottom portion of the molecule, that's going to make them a meso compound. It doesn't necessarily have to be the top and the bottom. You could have the left side of the molecule as a mirror image of the right side of the molecule. And then that's one thing that's going to be called an internal plane of symmetry. But then to confirm everything, you got to double check if you have an R and S enantiomers or chiral centers in there. So I'm going to go ahead and figure out the chiralities on these chiral centers here. So let's look at this particular one. And when I'm counting it, this is going to be 1 here. On the bottom, you're going to be 2. This is going to be 3. And your hydrogen is going to be 4. So it seems like it's going 1, 2, 3. It's going clockwise. But then remember, you would have to flip it because your hydrogen is coming out of the page. So when you flip it, it's actually going to be counterclockwise. So as a result, this is going to be S. So eventually it's going to be going counterclockwise. So it's going to be an S, and we can double check what's going on the bottom one. So on the bottom, I got 1 here. Your 2 is going to be still on the top. 3 is going to be right here. And then 4 is still going to be hydrogen. So when you going from 1 to 2 to 3, it seems like you're going counterclockwise, but then you would have to flip it or rotate it by 180 degrees because your hydrogen is coming out of the page. So when you flip it, it's actually going to be going clockwise. So it's going to be R, so I'm not going to draw the arrow there just because it's going to make it too crowded. So you have an R and an S in there. Anytime you have an R and S, you have one portion of the molecule mirror image of the other portion of the molecule. That's going to make it an meso compound. So both the relationship between A and B is not going to be the enantiomers. They are rather going to be your meso compounds. And sometimes you may not be given 2 different compounds to compare those as mesos. One compound is still going to be considered as an meso. If I just give you A itself is going to be an meso. What if I flip this OH and H position? Like, let's look at this next one here. This is not going to be an meso anymore, and there's a couple of reasons why it cannot be a meso. There is no internal plane of symmetry. If you see the top of the molecule and the bottom of the molecule, they're not mirror images of one another. And how do you know they're not mirror images of one another? Well, clearly this hydrogen and this OH, they are not going to be aligning with one another. And then same can be said on the left side. So no internal plane of symmetry in there. And then the other way you can check, you can rotate the molecule by 180 degrees. So if I go ahead and draw a mirror here, and then I would go ahead and flip this molecule. So right now, this molecule, I'm going to call this C here, call this D here. Okay, the relationship between C and D seems to be an enantiomers because the C and D, they are going to be non-superimposable mirror images of one another. And how they are not non-superimposable, well, I can go ahead and pick this molecule momentarily, and if I place it right on the top of that, you can see how you have these mismatches. Your H is not aligned with the H there. They are mismatches. So let me just go ahead and bring this back here. And then you can clearly see that when you put in a mirror in front of it, you have this hydrogen, they're kind of closer together. This OH is kind of closer together as well. So they seem to be in enantiomers, but just to double check things, you can go ahead and draw out the flipped version of it. So when I flip it or rotate it by 180 degrees, so what we're gonna get here? So I'm gonna go ahead and just to make this molecule right there, and I'll draw these lines as well. And then if I look at this OH right there, so when you flip it all the way, it's going to be right here. And that means your hydrogen is going to be up here. And then if I go ahead and change the color, this OH, when you rotate it all the way, it's going to be going away. And this hydrogen is going to be right here. So keep in mind, look at the color combinations. So then, let's call this C prime. What's going to be the relation between your C prime and the D here? So I'm gonna draw the mirror here. You can clearly see there are still non-superimposable mirror images of one another because you can have this OH and this OH right there and this hydrogen right there. So there are still non-superimposable mirror images, or another way of saying there are still enantiomers. So that's why they are not the mesos. So what we have in the earlier case, this B and A prime were not non-superimposable mirror images, so that's why they were not enantiomers. So in this case, they are going to be the enantiomers. So the relationship between C and D would be the enantiomers. Okay, what about skeleton structures? How would you figure out if a given skeleton structure is going to be a meso or not? So there's a couple of ways you can always do those. So suppose I'm looking at these three compounds and trying to figure out the relation between those three. Let's call this A, B, and C. And we can clearly see that we seems like we have an internal plane of symmetry there. We just have to make sure that it kind of matches, or the one side of the molecule is the mirror image of the other side of the molecule. But it does seem like we have three carbons right there on the left side. We've got three carbons on the right side, and that's going to be the story with all of these structures that I have drawn here. So I want to go ahead and figure out if any of those are going to be meso, and what's going to be the relation with the other ones if it is indeed a different than meso. So one of the ways you can do it, figure out their RNS configurations, and the other way is by looking at their reflections. If I focus on A, I can clearly see in A, I don't really have the OHs kind of pointed in the same direction. One of the OH on the top there, let's call this one here, that's going back into the page. The OH on the bottom is coming out of the page. So to make this a little bit more going in the same direction, I can rotate this molecule, something like this. So when I rotate it, your left side kind of stays the same, or another way of saying your uh, first OH stays the same, but what happens to the second OH? The second OH, it was coming out of the page, but when you rotate it by 180 degrees, it goes back into the page like this. Now it's easier to kind of compare if they are going to be the mirror images of one another. And it seems like they are indeed going to be the mirror images of one another, because now you have the OHs kind of aligning on the same side. Before, the OH didn't really align. This OH, and when we look on the bottom right there, there was really nothing to kind of replicate that. And then when we look at the OH1, we didn't really have anything onto this top right side to replicate that. So that didn't really match, but then you can always rotate it and see if they're going to be um, matching with one another. And I can do the same thing for this second one, and when I'm rotating the second one, I would get, let me just kind of go ahead and rotate this right side. So this OH is still going to be coming out of the page, and now this second OH was going back into the page, but now all of a sudden it's going to be coming out of the page because you just rotated it. And you can clearly see that we're still going to have an internal plane of symmetry where that OH is going to be the same. Now, those two molecules are interconvertible because I can rotate this molecule, this first one, by 180 degrees, and I'm going to get the second one. And that's why they are not going to be the enantiomers, but rather they are going to be the same compounds. And what I'm going to have to do to kind of double check this, I can go ahead and figure out their RNS configurations. And let me go ahead and erase a part of it to not make it too crowded. Focus on maybe this chiral center first. So this is going to be 1, that's going to be 2, that's 3, and that means your hydrogen is going to be coming out of the page. That's going to be your number 4. When you're following this 1, 2, 3, it's going clockwise, but then you would have to flip it because your hydrogen is coming out of the page. So it would be counterclockwise, so that's going to be your S. And we can clearly do something similar for this second chiral center. The OH is going to be 1, the left side is going to be 2, Your right side is going to be 3, and then your hydrogen is going to be going back into the page. So let's not draw that one. When you follow 1, 2, 3, it's going clockwise. That's going to be R. So you have an S and R, and that's exactly what we really need in case of a meso compound. We want to have 50% R and 50% S. Now when we check the other guy, when we're looking at the second one, this particular one, it's all of a sudden it's kind of flipped. So that's going to be your R here, and this one is going to be S. So double check, make sure you are able to get those configurations. So still, it's going to be a flip, and then as a result, this is going to be a meso compound because you have a first internal plane of symmetry, and the second you got one chiral center to be S and the other chiral center to be R. When we're looking at C, what's happening here? Well, this first one is going to be R, kind of similar to the B. And what's this going to be? The second one, second OH chiral center here, it's going to be similar to what you see in case of A, so that's also going to be R. So you have an RR here, so that cannot be your meso compounds. So the relationship between A and B are going to be the mesos. And then what's going to be the relationship, let's say, between A and C and relationship between B and C? Well, those are going to be your diastereomers, because remember, they are not mirror images of one another. Anytime you have two chiral centers or more than two chiral centers and two structures are not mirror images of one another, then they're going to be diastereomers. Also keep in mind your diastereomers needs to have at least two chiral centers, and also keep in mind your diastereomers is not only limited to the optical isomers, your cis and trans also kind of falls in the category of diastereomers. Okay, let's look at some of these examples I got here. You got to figure out if they gonna be making up a meso compounds or not. When I'm looking at this first example, I do see a internal plane of symmetry, so that's obviously the first requirement. The second requirement is gonna be you have to have two chiral centers. So since there's no chiral center on this one, it's not gonna be meso. What about this second one? The second one has an internal plane of symmetry where you can draw the horizontal line in the middle. And I got two chiral centers, one on the top there, and I got another one that's going to be on the bottom. And we can clearly see that these guys, the top portion of the molecule and the bottom portion of the molecule, they are mirror images of one another, where bromine aligns with the bromine there and hydrogen aligns with the hydrogen. So as a result, this particular compound is going to be meso compound, and you can always double check by figuring out what their configuration is going to be. So if I look at this yellow chiral center, bromine is 1, this is 2, that's 3, your hydrogen is going to be 4, so it seems like it's going counterclockwise, but then you would have to flip it because your hydrogen is on the horizontal, which means it's coming out of the page. So when you flip it, it would go clockwise, so that's going to be your R. And when you're looking at this green chiral center, this is going to be 1 here, 2 here, 3 here, 4. And following 1, 2, 3 in the form of circle, it's going clockwise, but then you would have to flip it to make go hydrogen back into the page. So as a result, this will be actually counterclockwise. So that's going to be your S. So you clearly have an S and R in there, and that makes it an meso. What about the next one there? Well, in the next one, I have an internal plane of symmetry right there where I got this chlorine is a reflection of the other chlorine on the bottom side, and then we got, I can say this OH is a reflection of the other OH that's on the bottom side. So this, since we have a total of 4 chiral centers, and the top portion of the molecule is the mirror image of the bottom portion of the molecule, that's going to make it a meso compound as well. What about something like this next molecule? Even in this next molecule, I got this internal plane of symmetry there. So since we have an internal plane of symmetry, we can double check by looking at the chiralities. So this one, when I'm looking at the chirality, this is going to be 1 here, 2 here, 3 here. So that's going clockwise. No need to flip it because your hydrogen is already back into the page. So that's not shown, so you don't really have to worry too much about showing it. So that would be R. And then when I'm looking at the other guy, so that this makes it 1 right there. That's 2, that's 3. So that's going counterclockwise, so that's going to be your S. So clearly you got an R and S in there. You got an internal plane of symmetry. That would make it meso. What about this next one here? You do have 2 chiral centers there, but there's really not any internal plane of symmetry because you can clearly see this one of the methyl group is coming out of the page here, and the other methyl group is going back into the page. So they're not going to be reflecting on one another, or they're not going to be the mirror images of one another. Um, so I can say no internal plane of symmetry. And then you can also always double check by figuring out where their configurations. And we already figured out what's going to be for this top one because that looks similar to what we have on the left molecule. So that should be R. What about this next one here? Well, this is going to be 1 here, 2 here, 3 here. And remember, your hydrogen now is going to be coming out of the page. That's 4. So it initially seems like going from 1 to 2 to 3 in the form of circle. It's going counterclockwise, but then you would have to rotate it or flip it to make this hydrogen go back into the page. So that would make it going clockwise. So that would be an R. So having an RR in the same molecule, it's not going to give you an meso compound. So this one is not meso. So that's how you're going to be determining the mesos.